Hi, welcome to the video lectures for your Introduction to Proof course. I'm Joe Fields. This is the first one. So let me first say a little bit about how the current lecture will be structured. There's a bit of introductory stuff. I just want to give you a couple of spiels about philosophy and why we're doing the course the way we are. There'll be a middle section about resources coming up, and then finally we'll actually start looking at some math in chapter 1.1, section 1.1 of the textbook. All right, so that's the plan. So first purpose, philosophy. You are about to embark on an enviable sort of endeavor. You're about to change from being a calculator to a prover. This is a little bit tough because I'm assuming your math major is deeply interested in math, and most of what you've done to date has been calculating things, coming up with answers, figuring out the minimum of a function on some interval, or calculating the amount of work it would take to fill some weird shaped tank full of water if it's elevated up in the air, integrals and derivatives and just regular algebra. All that calculational stuff you've learned becomes less important. You're going to be asked to do proofs soon, a transition to proofs. One of my heroes as a mathematician was a man named John Horton Conway. Conway once in my presence said more or less this: well, a proof is simply a convincing argument, isn't it? I loved the way he spoke. He had this really nice British accent, and he was brilliant. Unfortunately, he passed away due to complications from COVID-19 this past spring. But yeah, that's what we're after. You need to be able to make convincing arguments as to why the things you think are true are indeed true. Arguments that are often kind of artificial in the sense that there's certain well-established frames that you can do them in. There's certain forms of argumentation that people are expecting you to use. And so this course is about helping you to make that transition. But it is a transition that is a lifelong thing. I graduated with my PhD over 20 years ago. I've been a mathematician all that time. I've written a lot of proofs in that time, and I'm still learning things. There's still always more to know. So don't expect to go from not really being comfortable with proofs to being, I can prove anything. Fermat's theorem, don't worry, I got it. That's not going to happen. This is a transition. The idea of a course like this is it ramps you up, but it's not going to completely do the job. You're going to take other courses, like abstract algebra stands out in my mind, an area where you really hone your skills at doing proof, but real analysis, complex analysis, linear algebra, there's dozens of upper division courses. Well, maybe not dozens, but there are many upper level courses where you will continue to hone your skills at writing proofs. These lectures in particular are designed around the idea that your professor will be using a flipped classroom. So if you haven't run into the flipped classroom idea before, I think it's brilliant, and so I'm putting considerable effort into trying to help people use the flipped classroom idea. It basically, as the name implies, flips the roles of certain things. The passive activity of sitting in your chair and listening to somebody talk, that you can do at home. The more active activity of homework, where you're trying to solve problems, you're trying to write proofs, you're trying to figure things out, and you might get stuck, that happens during class time. So the professor or the TA or at least your fellow students will be available to unstick you if you get stuck. There's a term in the education lore called productive struggle, and I believe in productive struggle. Tearing your hair out a little bit it's a good thing, right? Working hard on something and eventually cracking it really is a great feeling. But unproductive struggle sucks. So really, we don't want you spending 6 hours on homework that you don't ever get anywhere on. That's why having the resources available during class time makes perfect sense to do your productive struggle stuff then. Unfortunately, or maybe just with good reason, there will also probably be additional homework that you'll do, at home. I can't help but just point out that a full-time college student is usually taking 12 credits, maybe 15. And a full-time person who's at work does 40 hours. So if you think of yourself as being a full-time, engaged full-time with college, then this course ought to be worth about a quarter of your time. Call that 10 hours. 3 hours of lectures and 3 hours of class time doing the second bullet type of homework. That doesn't add up to 10, does it? So yeah, we do expect you to be doing some other stuff. Hopefully, though, your struggle in the actual homework, the done-at-home homework, will be the productive sort, where, yeah, you may get stumped a little bit, but you won't be totally, at sea. You'll be able to get there. And worst case scenario is if you are at sea, you're in a setting now in the classroom where you feel more open to asking, right? You're not just sitting in your chair struggling to take notes to keep up with the lecturer. He's coming around and helping you with stuff. So you can say, hey, by the way, I couldn't get number 3 in last night's homework, and I'm sure he'll help, he or she. All right, so the book we're using here is an example of something called an OER, an Open Educational Resource. This is a kind of a descendant of the open source software movement. Open source means that the programming language source code for a project is open in the sense that other people can look at it. In fact, other people can adopt it for their own and steal. It's really not stealing if the other people are allowing you to do it. Open source software has been, and arguably in certain areas it has been a game changer. It's allowed things to proceed, to make it to market that wouldn't have otherwise. Most of the servers in the world are running Linux software, which was an open source project, is an open source project. So the idea that people can examine the source code and check it for errors and look for potential flaws in it and help fix those flaws if they discover them means that often open source projects are actually more secure than their brethren in the closed source world. Folks in open source often use the dichotomy between free as in beer versus free as in speech to describe some of the issues. Free beer is great, right? And this is free beer in that sense. You can get access to these lectures and to the books without paying a penny. So yay, free. But there's another sense that we use freedom, about the freedom of speech, the freedom of information. Materials in a book like this are the product of generations of mathematicians working on them, and they shouldn't be owned by anybody. This is the common birthright of all humankind. So it's free in that sense too. A major advantage to OERs, and I'm hoping to kind of enlist you folks as promoters, right? If you've got faculty in your home institutions who are maybe a little reluctant to use these open educational resources, they may need a little selling. And one advantage that is a big seller for people is that everybody will have the book day one. There will be none of that, dealing with the student who hasn't received his Amazon shipment 3 weeks in and is starting to fall way behind. It's really nice that they can just go to a website, download the thing off the internet, and have a PDF day one. Everybody jumps into action right away. Another advantage, this may take more selling, but it's still an advantage for your professors. If they dislike something about an OER, they're free, as in speech, free to grab the source code, modify it to suit their tastes, release their own version of the thing. Or maybe not release it, just make it available to their students. You, as students, can also contribute. I'll speak to that point a little bit in a sec. The layout of this book features a sort of recursive thing. One of my favorite profs in my graduate program was a man named Dan Bernstein, and he told me his philosophy of teaching followed a maxim that they used to say to speechwriters for politics, right? And it is this: tell them what you're going to tell them, then tell them what you told them. Three different approaches to the same information. Now, in this case, I feel that's slightly inappropriate because I'm going to sort of just barely introduce you to a topic. Then I'm going to revisit it a second time with more details and more. And thirdly, we're going to beat it down hard and really understand the topic in a rigorous way. So, but still, the idea of revisiting multiple times and gradually increasing the rigor as we go is important. With that in mind, chapter 1 in this book we're going to use, it contains almost all of the key ideas in the course, but not much detail. So don't get stuck in chapter 1. The point of chapter 1, honestly, is to sort of reserve space in your brain for some of the concepts. This is an idea. It's not borne out by research, but it is somewhat borne out by experience. I think that things are literally invisible to us when we don't know of their existence. If there's look, everybody's had this experience where you learn a new word, right? And then later that same day you hear the new word again. It's weird, right? It's not because suddenly that word started popping up out of the blue. That word was there all the time before. You just didn't notice it because you didn't know it. Our brains are finely tuned to helping us survive in the world, and if there's something that it can regard as extraneous detail, then it just pushes it aside, and we don't ever really become conscious of it. So chapter 1 is about first just making us conscious that certain things exist, reserving the ability for us to now think about that thing and not have it literally be invisible, and then we can proceed. So that's chapter 1. The rest of the book is that recursion and revisiting of topics. The main topics that we'll be looking at are logic, which is central to mathematics, sets, which is, in a sense, the same topic as logic, but it's also central to mathematics. Relations and functions. Those are, you're certainly familiar with functions. Relations are a sort of, I shouldn't say that way. Functions are a sort of relation, but both of these things are actually sets when it comes down to it. So they fall into the previous category as well. And finally, cardinality. One of the, this has to do with sets as well, but one of the really fun things at this stage in your career is you learn that infinity isn't just infinity. There's multiple kinds of infinity. And we kind of know a lot about infinity at this point in the progress of human knowledge. So that's kind of exciting. In between those sections about different topics, we'll have chapters on proof. And then, of course, as we go into the more advanced topics, we'll be able to use our knowledge of proof techniques. But there's a roughly an interleaving the topics, then a proof type, then more topics, then another proof type, etc. Okay, so resources, right. The book itself is available at GitHub for free. This is the link to it, and that's what the link looks like, or the linked object looks like. The actual thing says, follow this hyperlink that says the text. Click on that, and you now own the book. Do not look at the preliminary version in MBX. It is preliminary. There is also an exercise workbook. There are problems in the back of each section in the book, so you can get to them. You could print this out from here. It's also available on the Amazon site if you like. And I wouldn't print this one, just keep it online. There's a manual with hints and solutions. More hints than solutions. I like to leave you, struggling but productively. So I'll try to get you started on things, but not give away the whole game. Okay, so that's where you get the book. Let's look at the further resources. Oh, the source code. Oh, I've got a missing pause there. The source code is also available on GitHub. Let me quickly show you that as well. This is the main page for GitHub. Dozens and dozens of projects are available on GitHub. If you decide you want to help in the sense that I'm about to describe, you'll probably want to create an account on here. But you don't need an account to search. The project we're talking about is a gentle introduction to the art of mathematics. It goes by this initialism, GIAM, or GIAM. And there it is, the first thing on that search result. So this is the source code. Well, actually, these are a bunch of folders that contain the source code, but you get the idea. The way a student can help is in the second tab up here. Next to code, you see issues. You can open an issue. You can create an issue and say, hey, there's a typo on page 19, or I think you should put a problem like this into the exercises in chapter 3.3. Whatever you notice, add an issue. I may adopt it, I may not. You'll see that I still have a little bit of workload that goes back several years. Some of these actually have been done, and I don't know why I haven't closed them. Well, that's what'll happen though. If you raise an issue and I fix it, I'm supposed to close it. Not on me. I've got some unfinished business here that I'm showing you. All right, back to ourselves. The book is listed at the American Institute of Mathematics. There's this thing called the Open Textbook Initiative. And again, if you're interested in kind of selling your professors on this OER business, you can send them to this site, the AI Math, that's the American Institute of Mathematics. They have a thing called the OTI, Open Textbook Initiative, and it has, well, it's categorized by topics, but there's lots of books in all these topics. I had open the tab for linear algebra because this one here, my first course in linear algebra, is famous by a friend named Rob Beezer at the University of Puget Sound. There's a book in here, Abstract Algebra, Theory and Applications by Tom Judson. It's excellent. I feel like we should give Tom a plug too. A close friend of mine, Carl Dieter Christman, wrote this book, Number Theory in Context and Interactive. So the guy who wrote the Sage software, which we're going to be using in this course, wrote a book about elementary number theory in here. I believe it uses Sage. So actually, I think Carl Dieter's book does as well. But you see, there's lots of open source and books available for adoption. And these books that are on the American Institute of Math site have been vetted, at least to an extent. It's not like they've taken on the role of being the editor, but they have checked out that the things are truly open source, that they're definitely freely available, and that they've been classroom tested. So these are all pretty reasonable books to be using in a course. All right, back to the slides. Oh yeah, so you can also get the book in hard copy on Amazon. And I believe the workbook is also there on Amazon. I don't recommend that, but some people just like to hold on to the physical book, and it feels better to write in the margins on a real book. I hear you, so it's there. It's priced as cheap as I could make it. It turns out I do make a few pennies of royalties from this if you buy it at that price, but it was as low as it could go without. I couldn't set my own profit to zero. That's kind of a messed up thing in the system. All right, some other resources you need aside from the book is a calculator. I've got a frozen window here. There's a calculator that normally is live here on the page, but it is not currently. Anyway, one of those, a TI calculator. Got a little glitch in my screen recording software, I think. You'll need one of those, but that's very non-modern, isn't it? More importantly, you should have access to a computer algebra system. And you do. There is a freely available system called CoCalc, that provides a web-based interface. It's called a notebook interface to Sage, which is a hugely powerful computer algebra system. This is what it looks like if you just visit CoCalc directly. I have an account, so I'll sign in. Probably I should set this as homework for you. You should go to CoCalc and create an account here. Let me just make one request of you. If you create an account on CoCalc, it's going to ask you for first name, last name, email address. Use your academic email address so your prof can find you. Use the one for your school. And when it asks you to choose a password, don't screw around. Really give it a serious password. Write the password down and memorize it, and then, swallow the scrap of paper. No, it's not that bad. But security is an issue here. These folks at CoCalc are making a tremendous amount of computational power available to you. And if somebody steals your account and uses it for hacking and cracking, that would be bad. So don't do that. That was a 12-character password. Let's see. So when you first log into CoCalc here, you will be looking at a list of projects. You can organize things based on what they call projects. Inside of projects, you also have sort of the ability to create folders if you like, but I usually don't. I usually just plug everything into the project. I have in here a Sage worksheet. Let me show you what it looks like to create a new thing, though. The top of the page, well, the very top of the page is a list of the projects you've got currently open. I've only got the one, so no big deal. But the next layer of tabs is the file view, which we're currently looking at. You can look at a new view. This is where you could create a new thing. There's logs, there's searching, there's gears for setting things, and the actual current worksheet, which we don't need to look at right now. Let's look at the new thing. When you create a new file, and it tells you up top where it's going to be created, it will pre-populate the name of the worksheet you're creating with just a date stamp. That's fine, but I usually like to rename it, so it's something that I recognize. And then you'll select the type of thing. Or you can also just upload files, but I usually, throughout this course, the only thing we're going to be doing is Sage worksheets. But there are other options. For instance, if you know LaTeX, you can create LaTeX documents here. You can run a Linux terminal, command line stuff. If you're a professor, you can create a course and manage it. That's a functionality that requires you to pay. The account you get for free doesn't merge into a course. Well, no, the person who's running the course needs to pay. So I think you may be able to use your free account to get into it. Yeah, that's right. But anyway, there's a variety of different things, but we're always going to be using Sage worksheets. So here's a new Sage worksheet, and you'll see the interface just changed because we're in the worksheet now, but there's a couple of things that are fairly obvious what they do. Run it, stop it. If it's running out of control, you can kill the process. Restart it, which will reset all the variables. Basically, the way this looks is you're going to type some stuff. I don't know, how about 2 times 3? If you hit enter to try to get the answer, it just creates a new line, which at first is a little annoying, but what you have to do is hold shift down and then hit enter. And then it'll take a little while to think about this. And actually what's going on is it's initializing the project right now, making a strong connection. Finally, it came back and said, yes, 2 times 3 is 6. This obviously wouldn't be what we'd need if we only wanted to do 2 times 3. Oh, look at that. I typed pi. I wanted to get it to show me the digits of pi, and it responded with pi, which is not helpful, but it is actually the way the computer is thinking about pi. Pi is a real number. Its name is pi, not 3.14159. If you want to see the digits of pi, you need to do something else. And actually, this is a great place to show you a feature of Sage. every object in Sage, unless it's just a raw number like we typed there, the 2 times 3, is a object, which means that it has functions associated with it, which you can access by writing a period after it and then typing something. And if you don't know what to type, try hitting the tab key and it will give you suggestions. These are all functions that can be applied to the sort of object that pi is, which is a real number. And one of those functions, way down in here, is got a very short name. It's n. Pi.n is a way to get the decimal digits to nth precision, right? So if I type 100 in there, oops, I just hit enter without the shift. Let me hit the shift and enter. And now it'll show me pi. Does that look like 100 digits? Well, it's not. That's pi to 100 bytes of accuracy. If you wanted 100 digits, you can modify this n command and say digits equal 100. Hit enter. There's 100 digits. Does that look like 100? All right. Wouldn't have thought 100 fit on one line like that. If you want 1,000, not a problem. So, and did you notice how fast that was? This is screamingly fast software once the internet latency is taken out and it's connected to the server properly. So, well, we'll come back to Sage in a bit, but just wanted to give you a quick intro and demo of it. What else are we looking at? Oh, Desmos. I like Desmos a lot. Desmos is a fun utility for graphing. You know, the TI-83 that I use, if I need to graph something and I don't have a computer around, certainly I jump in and use that. But Desmos lets you use colors. You can get it on your cell phone, so you will probably almost always have it with you. I do recommend signing up for an account here, or you can do what I do, which is just log in with your Google credentials, and you're in. That allows you to save previous graphs. I've got all kinds of graphs on here that I've used before. You need to see that. And you can do stuff like you can do with a graphing calculator. For instance, you can plot a point. If I wanted, I could put a label on that point, apparently. Yeah. That's kind of cool. I didn't know that I could do that. How about if I just put the label on and don't have that? Then it gives me the default label, which is the actual coordinates of the point. That's kind of cool. You can plot functions, y equals x to the second, for instance. Oh yeah, and y equals x squared goes through my favorite point. You can plot things that are not functions, and this is something you can't do on the graphing calculator. For instance, there's x cubed minus x minus y squared equals 1. That's not a function. You can tell that's not a function, right? You know, remember the vertical line test? So that's not a function. I thought I may need to play around with something here. 2 times that? Oh, there we go. 3 times x will look cooler. Another thing that you can do with Desmos, which I really absolutely love. Notice I was like trying out different values for the coefficient of x in this thing. You can put in a letter, and it'll add a slider for that. Right? So now I've got a parameterized function. I can change the parameter and get different things. These are all family of curves that are related by just changing the multiplier on x. None of them are functions, and they're easy to plot in Desmos. It can do other stuff. For instance, it's cool about shading up above or below a graph. You can do a lot of neat stuff with Desmos. So I encourage you to get on here and start playing. And you can also look through, I think there's a way to look for previously shared graphs that people have. These are like all my things, so maybe not, but no. Anyway, if I were to sign, yeah, here's if you're signed out, these are the example graphs that you might be able to find and see how the people did things. Okay, so that's Desmos. There's the giant book. I think that's I'm going to go back to our slides. GeoGebra for geometric constructions. I'm not going to show you anything about that today. Let's get into section 1. So the basic sets that we're going to work with in this initial chapter are the natural numbers. I take 0 as being a natural number. Some people do not. Make sure you know what kind of person you're dealing with when you say naturals. Naturals are the numbers we use to count things, and I would argue that there are certain collections that have no elements, so you should include 0 as a natural. Also, the piano axioms for the natural numbers, which are the sort of official axioms. The first one is 0 is in n. So yeah, but historically, the naturals did not include 0. 0 was created relatively recently, to be honest. So the ancient Greeks didn't consider 0 to be a natural number, but in more modern times, we usually do. The integers, which are not written with an I but with a Z, are sort of an obvious natural extension of the naturals. They include negatives as well as positive real numbers, positive natural numbers. The rational numbers, these are the numbers you can get with fractions. So the real numbers, these are really hard to describe. The real numbers consist of one-dimensional numbers that can be used to represent physical quantities. I think that's the best way to say it to you at this time. If you've got an object that has a certain weight, you know, I've got a water cup here, weighs about 300 grams. Probably not. But anyway, you know, it could be 301.297 grams. That's a real number. And finally, the complex numbers. The kind of numbers that come out of the quadratic formula. If you plug in something in the quadratic formula and that part under the square root is negative, you get a complex number. In the course of discussing these numbers, these sets of numbers, we're going to need to talk a little bit about the way we denote sets. So yeah, roster form is just a listing. If you wanted to, for instance, look at the first set we talked about on the previous slide, the natural numbers, the way you could write that with roster form is this. You use the curly French brace that you always use for sets, and then just start listing the elements. Unfortunately, you have forever to work on this, so typically after you establish a pattern, you put an ellipsis and triple dots to say that pattern continues, and then you end it with a French brace. If you've got a finite set, you should list everything, unless it's super long. Like you know, if you had 80 elements, you wouldn't list them all, but you'd set up a pattern, put the dot dot dots, and then list the final thing. The dot dot dots can go both ways. The integers, for instance, I mentioned they not only include 0, they also have negatives. The way I would write that is set up my braces to begin with, put 0 in the middle, and you can do negatives to the left and positives to the right. And have it go dot 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 that way. Another approach to that is to start at 0 and then do your plus and minuses both heading to the right. So you could certainly re-express the integers this way. It's 0, then there's 1, then there's minus 1, then there's 2, and then there's minus 2, and so on. Just two different ways to express the same thing. As long as you can see the established pattern and see how it could be continued, you've done the job that needs to be done for roster form. Okay, so there's an example of roster form, a silly one, because the things in a set don't have to be, you know, numbers. They don't have to be, so in this case it's the suits in a standard deck of playing card. Sets are always denoted with curly braces. Those are the examples I just did, the one that was here in the slides. Those are you will sometimes hear these referred to as French braces. I always call them curly. Anyway, set builder notation is a different way to describe things, the elements of a set. Instead of just laying them all out, listing them, you just name a property that the things that are in the set will have. So there's an example. X such that, that vertical bar in the notation right there is read as such that. And then we've got a compound inequality. X lies in between 1 and 4 is how I would say that works. That's actually got an issue. What kind of number are you talking about for X? Because if you had, well, the problem is I haven't said what kind of number it is. The solution is you should say what kind of number it is. That's called a universe of discourse. So here's two different set builder notations that use the same compound inequality. X in R such that X lies between 1 and 4 versus X in Z such that 1 lies between X and 4. Those are very different, right? The one is an interval. If you were familiar with interval notation, it would be the interval from 1 to 4 with the square braces at the ends. Versus the other set, well, that's just I'll do the roster form of it. It's the integers between 1 and 4. So they're vastly different. This has 4 elements. This has infinitely many elements. Right? Okay. This is a recreation of something from the textbook, a kind of translation, trying to build up a facility with looking at one of these set builder notations, and really all mathematical notation, and being able to quickly read it off. So let's just point out the things in this that are problematic. If the symbol Q is being used, at some point before you saw this thing introduced, you would probably say, we call the rational numbers Q, and then you give a precise definition of it. But Q equals curly brace, A over B, the such that bar. So what are the elements of this that we haven't run into before? The curly brace is unusual, this vertical bar for such that. I've seen fractions, right? So when I see the A over B translated into fractions of the form A over B, that's not a big deal. But this weird vertical bar becoming the word such that, that's interesting. Is everybody, it disappears if I try to highlight it. That symbol right there, that it's kind of a stylized E, stands for in or as an element of. So we've got 2 uses of that. Q is equal to the set of all fractions of the form A over B such that A is an element of the integers and B is an element of the integers. And in this case, we're defining the set of rational numbers. You all know that you can't divide by 0, right? So the B, the bottom part of that, has to be non-zero. And then you don't need to say anything for the final curly brace. Okay, so let's end this with a couple of comments, a couple of examples about doing some operations in the sets. I think we're all clear on how to do operations in the naturals and the integers. That's elementary school level. Fractions, that's what the set Q really is. So the set of fractions, rational numbers. Before we get started, you gotta make sure that everybody's clear on this point that I thought was deserving of writing in all caps. Not every real number can be expressed as a fraction. Lots of times people think they can, but in fact, they can't. So let me illustrate this with your graphing calculator. You may not be familiar with this, although I hope you are. There's a button on the calculator that will convert things to fractions. So I don't know, how about 1 divided by 3? That is a fraction, right? But once it's in the calculator, it becomes 0.3 repeating. If I multiply that by 2 divided by 5, okay, I got some fractional thing. 0.1 and then 3 is going on forever. The button I'm referring to is under the math submenu. So do you see the math button right there? Hit that, and it's actually the first thing that comes up in the math submenu. It's arrow frac. So I hit arrow frac and then hit return. And it turned my 0.13333 into 2 over 15. Now let me just point out, not every number will be able to turn into a fraction, but most numbers can be. Well, most numbers that you can write on a calculator can be. Like if I had 0.14528, right, there's a number. Doesn't seem like it should be a fraction, right? But go math and turn it into a frac, and you get 454 over 3125. I'm surprised. Let me do that again. 0.12. Try to look for one that's not going to get to a simplified fraction. That's what I was sort of hoping for. A random decimal that terminates, like 0.127, you can already write it as 127 over 1,000, right? 127 over 1,000. That's what it means to be a rational number. You got two integers. 127 is a whole number. 1,000 is a whole number. So, boom, any terminating fraction can be expressed as a rational number, as an integer over an integer. There are other numbers that can be expressed as fractions. Let me just give one of my favorites. 1 divided by 7. 0.142857, and then 1429. Now you probably know this, that 9 is just rounding because it's we're at the last digit of the calculator's accuracy. What's really going on here is 142857 repeats. That's 14 and the first few digits of 2857. A repeating decimal like that, where there's some snippet of digits that gets repeated over and over again, is always a rational number. And it's actually not too hard to see how you can do that. Well, that's something we'll save for later. But decimals that terminate and decimals that have a repeating pattern, those are rational numbers. If a thing doesn't terminate and doesn't have a repeating pattern, then it will not be a rational number. Take a look at, for instance, this famous irrational number, square root of 2. Supposedly, I think I've got this story right, the Euclid, or maybe it's Pythagoras, finally proved that this was not a fraction, and they sacrificed 100 bulls, 100 oxen, to celebrate that. Sounds weird, but that actually was kind of a common way to celebrate big events in ancient Greece. Have these giant sacrifices of animals to the gods. Anyway, 1.414213562. I don't see a repeating pattern, but there's no reason the repeating pattern couldn't be really long, longer than the digits on the calculator tell me. But if you try the toFrac button, it doesn't do anything. It just repeats the decimal. So some numbers can be expressed as fractions. Other real numbers cannot be. Important point. So yeah, I mentioned this. The ancient Greeks were initially confused about this. It was thought for quite a long time that to be a number meant to be a ratio. They didn't know anything about the complex numbers, but it was an eye-opener when they realized that there were real numbers which were not rational. Okay, so I said I was going to do operations in these sets. Let's do some operations in the rationals. How do you do multiplication of two fractions? I know you guys know this, so let's just deal with the easy case first. If you have a over b is one fraction and c over d is another, then their product is ac over bd. You just multiply the tops, you multiply the bottoms. If you did, and this is a little bit weird because usually we think of multiplying as harder than adding, but if you did that same operation, that same style of operation with sums, if you had a over b, and let's just make a square symbol here in between it, and c over d. Okay, so that would mean you would have to add a and c in the top, and you would add b and d in the bottom. I hope you know that's not how you add fractions, right? But that is something. It is an operation you can create with two fractions, and it in fact has a name. This This is probably a non-standard symbol for it, but what I'm doing right there is known as the mediant of two fractions. And it's an interesting number. It's guaranteed to lie between the two of them. It is a mistake to think that's the sum, but it is actually a reasonable operation in a certain sense. If you're adding batting averages, that's the right thing to do. If I give you an example, suppose I'm at bat in one game 4 times, and I get a hit. So I have 1 for 4 in one game. And in another game, I get 2 hits, but I'm at bat 5 times in that game. So the mediant of these would be add the tops and get 3, and add the bottoms and get 9. So I'm batting .333, right? I'm batting .333, batting well over 300. Man, I'm a good hitter. So yeah, but do you see why this is the correct way to add batting averages? Because we want to be dividing by the total number of at-bats, and we want to, the thing we need to divide by is the total number of hits. So what we've got here is for the 2 games together, 3 hits out of 9 at-bats, which is the correct thing to do for adding batting averages, but it's not the correct thing to do if you're adding, pieces of pie or something. So how do you, in fact, add rational numbers? The quick way to do it is to simply not worry about a common denominator, but use the product of the denominators. So you can put BD in the bottom. And then, let's see, in order to get this side to be over BD, I'd need to multiply top and bottom by D. That means the top numerators would be AD, and the second fraction's numerator would be BC. Okay? You can find a real common denominator or a least common denominator, but this is going to do the trick if you're working in general like this, where you don't actually know what the numbers are. That's how you get a sum. That should have been reviewed, but it's not necessarily the case that products and sums in the complex numbers will be a review. So let's quickly talk about that. First of all, let's write the set builder notation for the complex numbers. C is equal to, or is defined to be, the set of all expressions that look like A plus BI, where A is a real number, and I'll just write out the word and for now. B is a real number. And lastly, what is that I that's in there? I squared has a value -1. That is, I is the square root of -1, but I prefer to write it in the reverse way. So that's what the complex numbers consist of. If you've played with the quadratic formula before, sometimes these come out of it. In fact, that's one way to think about it. It's the sort of things that you'll get out of the quadratic formula when the part under the square root ends up being negative. So if I have 2 of these, how about A plus BI? That's one complex number, and a second one, I need to use different variables in there, but how about C plus DI? Just like I did for the rational numbers. If I'm going to add, however, adding for these complex numbers is the thing that works nice. You just add the parts that don't have an I, and you add the parts that do have an I, and you're done. So you get A plus C plus B plus D, and those things both had an I on them, so I can factor that I out. This operation is called component-wise addition, very much like these operations. That's called component-wise multiplication, and in the mediant we were doing component-wise addition. Component-wise operations are pretty nice. To multiply in the complex numbers, you have to use the FOIL rule. In my slide, I forgot to pump the slide forward, but we just did component-wide addition. And I said FOIL, but notice that I wrote FLOY. there's actually a good reason for that. The Floyd method looks like this. You have a plus bi times c plus di. It's just that I would rather multiply first and last first, and then multiply the outer times inner. Why? Well, outer times outer is going to give us AD times I, and inner times inner is going to give us BC times I. Those things are both going to include an I in them. The first times first is clearly just real. It has no imaginary unit on it. It's AC. Last times last is BD times I. But remember that I squared is minus 1? So that's really just negative BD. When you Floyd this out, you get AC from first times first, negative BD from last times last, and then the things that have an I in them are outer times outer, AD, and inner times inner, BC. Those both have I's. So we can factor the I out and get something like that. Awesome. So that's how we algebraically add and multiply complex numbers. This can also be thought of as a geometric thing, which I believe is well, we're almost done for today, but geometrically, what you do is you plot the point, the complex number. This would be the point whose coordinates are a, b, but that's thought of as the complex number a plus bi. If you're doing this plotting, this is no longer the x-axis and that's the y-axis. Rather, this is called the real axis and this the imaginary axis. But it's the same xy plane, right? It's the same pairs of real numbers make up a point, or pairs of real numbers make up a complex number. The complex number a plus bi and the complex number c plus di are added by, well, this is the same trick they use for adding vectors. Imagine taking this complex number and sliding it along here until its tail, or what used to be at the origin, is now at the point AB, and you get a new point, right? You could have done this either way. You could have slid AB over so that its tail lined up with the head of C plus D, I, or vice versa. And you get a so-called parallelogram, right? I shouldn't say so-called. This is a parallelogram, but the way of graphically adding two complex numbers, or graphically adding two vectors, is called the parallelogram rule, because you create a parallelogram in it. So this complex number has coordinates that we found before, a plus c plus b plus di. Writing off the screen there. So you can think geometrically about adding complex numbers. You can think algebraically, just component-wise addition. The multiplication is interesting, and I think we'll leave it at that because we're going to return to that and see it next time. Lastly, we got to talk about the trichotomy property of the reals. First of all, hopefully you've heard the word dichotomy. Especially people use the phrase a false dichotomy. My favorite false dichotomy is the saying, you're either with us or you're against us, which is nonsense. There's a third option. I could be completely ambivalent about you, right? I know the people that would say you're either with us or against us think that there is not a third option, but really there is. Trichotomy is, well, actually, I guess I should have mentioned the etymology of the word. Dichotomy, di is a Greek root meaning two, and chotomy, well, koto is for cutting. So this is a division or a cut into two. Trichotomy is then obviously a cut into three. So what does it mean? In the reals, it means every real number is either bigger than 0 or less than 0, or it is 0. So positive, negative, or 0. That's the three options for a real number. And any subset of the real numbers inherits that property. If every real number is in one of those three categories, and say the rational numbers are included amongst the real numbers, then they're in one of those three categories. It is a little bit weak for the natural numbers because there aren't any negative ones here, but you do still get 0 or positive. So yeah, you still could say you satisfy the trichotomy property. You're in one of those three groups, just not actually appearing in the negative ones. There is a fairly standard way to denote the sets restricted to some of these parts. I think I'm just going to show you this for the reals. R plus means the positive real numbers. That's a superscript plus sign. R minus is a fairly obvious way to talk about the negative real numbers. R non-neg, that means, what does that mean? Not the negative numbers. So it includes 0 and the positive ones, just doesn't have the negative ones. And lastly, you will probably run into this one in abstract algebra. If you put a star on any set, it means take away 0. So the negative real numbers together with the positive real numbers, those make the area, the set that's called R star. That actually forms a group. When you get to abstract, you'll get to hear about that more. Okay, we are out for today. Thanks for getting through all this. We'll be back with lecture 2 covering section 1.2 in a moment.